In this guide, why unsigned OAuth authorization responses are vulnerable to tampering, how JARM signs the entire response as a JWT bound to client and server, what the JWT claims and response mode parameter look like on the wire, and when FAPI 1 and FAPI 2 require it. Identity Expert, powering you to be an expert in identity. Today we are covering JARM JWT Secured Authorization Response Mode, pronounced JARM. Here is what most developers do not realize. When an authorization server redirects your user back to your application with an authorization code, that code arrives as a plain query parameter. There is no signature. There is no proof it came from the authorization server you expect. There is no guarantee a browser extension, a malicious proxy, or an attacker who knows your redirect URI did not swap it. JARM closes that gap by wrapping the entire authorization response, the code, the state, every parameter inside a signed JWT before the redirect ever hits the browser. Your client verifies the signature, checks the issuer, checks the audience, checks the expiry, and only then extracts the code. JARM is not theoretical hardening. It is mandatory in FAPI 2, the security profile that underpins open banking in the UK, Brazil, and Australia. If you touch financial APIs, regulated data, or high-assurance OAuth flows, this is the spec you need to understand. Imagine you order a certified bank statement to prove your balance to a landlord. The bank prints the document, seals it in an envelope, and stamps the seal with an official notary stamp. When the landlord receives it, they can verify that stamp against the bank's public registry. If anyone opened the envelope and changed a number, the seal is broken. The landlord knows immediately the document is not authentic. Now imagine instead the bank texts you the balance as a plain message. No seal, no signature, just digits in a chat thread. Any app on your phone can intercept that message, rewrite the numbers, and forward it on. The landlord has no way to know the number has been changed. Standard OAuth authorization responses are that plain text message. The authorization code arrives in your browser as a raw query parameter. Anything running in the browser, an extension, a script on your page, a compromised dependency can see it, potentially intercept it, or in some attack scenarios substitute a different code entirely. JARM is the notarized envelope. The authorization server seals the entire response into a JWT it signs with its private key. Your application verifies that signature using the server's published public key from its JWKS endpoint. If a single bit of the response was altered in transit, the signature check fails. The response is rejected before your application processes a single parameter. Let us be specific about what standard OAuth leaves exposed. When the authorization server redirects the user back after a successful login, the response looks like this. Your callback URL followed by a question mark, code equals some opaque string, ampersand state equals whatever you sent. That is it. 4 problems live in that URL. First, response tampering. There is no signature. A malicious browser extension or proxy sitting between the authorization server and your application can modify any parameter. It can swap the code. It can strip or alter the state. Your application has no cryptographic proof of what the authorization server actually sent. Second, mix-up attacks. Suppose your application integrates with multiple authorization servers. An attacker who controls one of those servers can return a code issued by their server to your callback when you were expecting a code from a completely different server. Without issuer binding in the response, your client cannot tell them apart. It might send that code to the wrong token endpoint, or worse, an attacker-controlled one. Third, code injection. An attacker who obtained a valid authorization code, for example, one issued to a different session, can try to inject it into your callback URL before your application processes it. Without audience binding in the response, your client cannot prove the code was issued specifically for it. Fourth, code leakage. The authorization code appears in browser history and in server access logs via the HTTP referrer header for any third-party resource loaded on your callback page. JARM addresses all 4 by moving the response inside a signed, issuer-bound, audience-bound, expiry-limited JWT. Here is the JARM flow step by step. Step 1. Your client application sends an authorization request to the authorization server. Critically, it includes the parameter response_mode equals JWT. That single parameter tells the authorization server to respond with a JARM JWT instead of plain query parameters. Step 2. The user authenticates and grants consent. The authorization server prepares the response, packages the authorization code, the state, and any other parameters as claims inside a JWT payload, and signs the JWT with its private key using an algorithm like PS256 or EAS256. Step 3. The authorization server redirects the user's browser back to your callback with a single parameter. Response equals the signed JWT. The code is no longer visible in the URL, it is inside the JWT. Step 4. Your client application receives the JWT and immediately verifies it. It fetches the authorization server's public keys from the JWKS endpoint, verifies the JWT signature, confirms that the IS claim matches the authorization server it initiated the request with, confirms that the OAuth claim equals its own client ID, and confirms the EXP claim has not passed. Step 5. Only after all checks pass does the client extract the code and state from the JWT payload. Step 6. The client presents the code at the token endpoint, along with the PKCE code verifier, and exchanges it for an access token. The JARM JWT structure is straightforward. The header carries the algorithm and key ID. The payload carries IS binding the response to the authorization server, OAuth binding it to your specific client, EXP limiting the replay window, the code itself, and the state, all sealed under a cryptographic signature. Let us look at what JARM looks like on the wire. The authorization request is a standard JET to the authorization endpoint. It includes response_type equals code, client_id, redirect_URI scope state, a PKCE code challenge with method S256, and the critical new parameter, response_mode equals JWT. The authorization server's redirect response carries a single response parameter containing a compact signed JWT. Inside, when decoded, the payload contains 5 claims. IS is the authorization server's issuer URL. This is the issuer binding that defeats mix-up attacks. OAuth is your client ID. This is the audience binding that defeats code injection. EXP is a Unix timestamp set to somewhere between 60 and 600 seconds from now. This limits the replay window. Code is the authorization code itself, now hidden inside the signed artifact rather than visible in the URL. And state is the session-bound nonce you sent in the request, carried inside the JWT so it cannot be stripped or altered independently. The JWT header specifies PS256 as the signing algorithm and references the key ID from the authorization server's JWKS endpoint. Your client verifies all 5 claims before trusting anything in the response. Skipping signature verification or ignoring the OAuth claim means the client gains none of JARM's protections. Verification is the entire mechanism. JARM is designed to neutralize 3 categories of attack that the standard OAuth redirect flow cannot address. Threat 1. Response tampering. An attacker with access to the browser through a malicious extension, a compromised device, or a non-TLS segment can modify the authorization code or any query parameter in a plain redirect. JARM defeats this with a JWS signature over the entire response payload. Any modification to any claim after signing invalidates the signature. The client detects the tampering immediately on verification and rejects the response before extracting any parameters. Threat 2. The mix-up attack. This attack targets clients that interact with multiple authorization servers. An attacker who controls one authorization server substitutes a code issued by their server at a callback where the client was expecting a code from a legitimate server. Without cryptographic issuer identification in the response, the client cannot distinguish them. JARM's IS claim carries the authorization server's issuer URL inside the signed JWT. The client must verify that IS matches the server it sent the original request to. A mix-up attempt produces an IS mismatch, and the client rejects the response. The OAuth claim provides the same binding at the client level. A code issued to one client cannot be replayed against another. Threat 3. Code replay. An attacker who captures a valid JARM JWT and attempts to replay it later is blocked by the short EXP claim. Typically set to 60 to 600 seconds. The expiry combined with PKCE's code verifier binding at the token endpoint and optional one-time JTI tracking means a captured JARM response becomes useless within minutes. As of 2026, JARM's adoption trajectory is clear and accelerating. In the regulated financial sector, JARM is not optional. FAPI 2 security profile finalized in 2024 mandates JARM for all authorization responses in open banking deployments. The FAPI 2 attacker model explicitly calls out authorization response integrity as a required property, and JARM is the mechanism that satisfies it. The older hybrid flow pattern from FAPI 1 Advanced, returning an ID token alongside the code in the response, is being retired for new deployments in favor of the cleaner JARM approach. In the broader OAuth ecosystem, OAuth 2.1 does not mandate JARM but consolidates PKCE as required for all clients. JARM composes naturally with PKCE and is the recommended response mode for high-assurance flows. RFC 9207, published in 2022, defined a lightweight IS query parameter on plain redirect responses as a partial mix-up mitigation. JARM supersedes it for regulated deployments because IS inside a signed JWT is cryptographically bound rather than advisory. For real-world adoption, most commercial authorization server vendors, Curity, Authleet, ForgeRock, Ping Identity, and Keycloak with extensions, now ship JARM as a first-class feature. Open banking ecosystems in Brazil, the UK, and Australia already require it. The EU's EUDI wallet proposals are driving further adoption across Europe. Next on identityexpert, CIBA, client-initiated backchannel authentication, the flow that separates the authentication device from the consumption device entirely. Subscribe so you do not miss it. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to identityexpert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.